Hi, chemistry students. It's a great joy for me to start to talk to you about kinetics. This is actually one of my favorite topics in all of chemistry, and I'm hoping that you'll see not only the usefulness of understanding how quickly chemical reactions occur, but you'll also see the beauty of some of the mathematics that we'll talk about. You'll see the elegance in the physical model that we have for why certain reactions go faster than other reactions, and why these various factors such as temperature and concentration can affect the rate of reaction, because this chapter really lets you think about molecules moving around and bumping into each other and leading to chemical transformation. So in today's short lesson, I'm going to be covering just a bit of the chapter, but I wanted to start with an introduction to all of chemical kinetics, and then we're going to move on and we're going to be looking at defining rate. We'll be looking at how to define rate, a single rate that will govern the entire chemical reaction so that we don't have to be bound to the individual rates of the chemical reactants or the chemical products. And then we'll briefly look at the difference between differential rate laws and integrated rate laws. And so we'll talk about why we have these two things and what purpose they serve. So I'm hoping this video will fit in to the other videos that we have posted on Canvas, and you can watch each of them to put together the entire puzzle that is chemical kinetics. So first of all, here are objectives for this chapter. These are the qualitative objectives. What we want to do first is understand what it is that causes a reaction to go faster or slower, what various variables, and here you can see a list. We want to have a list in our head so that we can predict the the effect of changing these things on the chemical rate of reaction. But we also want to have a more intuitive, logical understanding of why something like the temperature increasing or the concentration increasing, we want to understand why that can cause a chemical reaction to move more quickly, and why catalysts can actually increase the rate of reaction without being used up. These are deep concepts in science and in chemistry, and we want to be able to think about them mechanistically, using our understanding of physics and the logical consequences of molecules hitting each other with a certain orientation and speed to predict what will happen with a chemical reaction. So briefly here, we'll won't spend a lot of time on this in this slide because the book does a good job of explaining the factors that affect the speed of reaction, but there is an intrinsic rate that is related to the chemical reactants in a particular system, and so different reactants react at different speeds. The temperature increasing and causes the rate to go faster. I think you might be aware of this. And having a higher concentration also speeds up the reaction. I think this also is somewhat intuitive for most folks. And then the presence and absence of catalysts. If you haven't come across the definition of a catalyst before, it's a pretty interesting chemical. It's something that is present in a chemical reaction mixture that causes the reaction to go more quickly, but is itself not even part of the reaction. What we'll find out later is that often catalysts are reactionary intermediates. They're substances that participate in one of the series of chemical reactions that happen when two, say, reactants come together, but which don't ultimately end up being consumed by the reaction. In other words, they're generated in the process of reacting, and then they're used up in the process of reacting. So their net concentration remains the same. Maybe I said that backwards. They're used up and then regenerated is maybe a better way to say it. At the end of the chapter, we'll be looking at something called collision theory, which looks at the mechanism of reactions. We'll talk about the various factors that lead to a chemical reaction going more quickly. And we'll also talk about specific reaction mechanisms. Turns out that there's a great line of work you can get into, which is basically just figuring out why reactions occur the way they occur. Very theoretical, very computational, very creative. So if you don't want to just be in the lab all the time, not that there's anything wrong with that, but if that's just not your personality and you wanted to be behind a computer thinking deep thoughts about chemistry, then this is something that you can get into. If you want to be in the lab and actually finding out how it really works, that's a fine line of work in chemistry too, and it's a good field that we can basically do both those things. So we're going to spend a lot of time in the chapter looking at these quantitative objectives, and today I'll be looking at rate laws and integrated rate laws, and we'll be briefly looking at how we define reaction rate in terms of just having one rate for the entire reaction. But in later videos and in some of the videos that are currently posted to Canvas, we'll be looking at some specific mathematical methods, including the initial rates method for determining the order of a reaction. And we'll be looking at some ways to take laboratory data and determine fundamental chemical properties such as the rate constant and the activation energy. Turns out that there is some pretty cool graphing techniques you can use. Just taking regular data like temperature data and pressure data, temperature data and concentration data, you can take these sets of data pretty easily, and then you can get these fundamental physical quantities out of it. So if you've ever wondered how you find out something like the activation energy, this is a chapter that can help to answer that question for you. So briefly, this is defined in more detail in another video that is on our Canvas site. The way we define rates in terms of a chemical reaction is primarily in terms of a change in concentration over a change in time. And this is a bit of a complicated definition in the sense that a concentration is itself a ratio. So it's kind of a ratio of a ratio. But it is something that I hope you're more familiar with, concentrations being something we've discussed now for a month or so. And let me just mention now that it doesn't always have to be concentration change. It could be a change in pressure. It could be a change in amount. There's nothing essentially, there's no reason we have to limit this to concentration. It's just that this is a nice way to think about most chemical reactions. Most of the ones we care about, whether they're happening environmentally in our waterways, our oceans, or sewer systems, or if they're happening biochemically in our bodies, or if they're happening in something we care about like food. Most of these are systems that you have one chemical that is dissolved in water or some other solvent. So most concentration data is really useful. And so we're going to focus in this chapter on concentration data. And the definition of rate is going to be always positive by definition. And we're going to start talking about reaction rates as being, they're just being basically one rate per chemical reaction. And so I wanted to take a minute and look at this example chemical reaction. This is an example where we have nitrogen dioxide decomposing into two new substances, nitrous oxide and oxygen. And as you can see, and as you might guess, the nitrogen dioxide, as it decomposes, it's going to decompose at a certain rate. Two of these NO2 molecules are going to produce two NO molecules and one O2 molecule. And since only one O2 molecule comes from every two NO2 molecules, you might guess that the rate of appearance of O2 is 1/2 the rate of disappearance of NO2. In other words, O2 is appearing at a different rate than NO2 is disappearing. And the other video that I posted goes into a lot of examples of how you get this. But what I want to show here is that basically this rate equation, what we have is we have just one rate that is equal to the rate of disappearance of the NO2 divided by the coefficient here. And it's also equal to the rate of appearance of the O2 divided by the coefficient. And what I want to focus on here is, why do we have this 2 and why do we have this negative sign? Now, the basic answer to both of these questions is that if we define rate to be always positive, then what we need to do is look at what this number would be. The change in NO2 over time, since NO2 is a reactant, it's being used up, it's decreasing over time. So the delta NO2, or the change in NO2, is going to itself be a negative number. So if we want our rates to always be positive, and we have a negative number here, we're going to have to add a negative in the front to make the rate positive. So that's the role of the negative sign here. And then second, if we want this equation up here to have basically just one rate, and we don't want it to be, you know, having one rate for NO2 and one rate for O2, we want one overall rate, it makes sense to just divide away every single coefficient in the equation. And so what the 2 is doing here, this 2, is basically, it's bringing this NO2 change down to be the same as the O2 change. And if we were to write the, you know, a different rate for the rate of appearance of NO, we would also divide the the delta NO over delta T, we would divide that also by 2. So we would also be dividing this 2 away. So that's the basic idea here as to why we would have these all equal to each other. Basically, we have one rate, and we're just going to define it as being equal to the rate of the concentration of reactants divided by their coefficients. And then the one extra step is that we're going to put a negative sign here for reactants, just to make sure that the overall rate is positive. And just as a bit of a teaser for later, I want to point out for those of you that have taken calculus that we can write change values using differentials. So what I have here is I put dNO2 over dt. This is the infinitesimal differential as you take the limit going to 0. This is the tiny little bit of incremental change that you might get if you were going to write this in terms of calculus. And in a later video, I'll be basically posting a way that we can take one of our rate laws and we can perform a bit of calculus on it, and we can turn it into an integrated rate law. So just a bit of a teaser there for what's coming up next. All right, let me erase this stuff and we'll move on to the takeaway here being, oh, I'm sorry, not the takeaway yet. Here's an example. So if you haven't done this yet, I would encourage you to just pause the video, take a moment and see if you can write the rate of this chemical reaction. And what you might want to do is think of writing it in terms of the change in concentration for each reactant or product. So do that, come back, and then I'll go ahead and solve it here. So the rate of this chemical reaction is going to equal, well, if I start with just this one, I can say it's going to equal the minus delta concentration of H2SO4. Again, just a reminder that these brackets mean concentration. So this is just a shorthand way of saying concentration of. The rate of disappearance of H2SO4 over time, that's going to equal the rate of the overall reaction. And the rate of disappearance of the other reactant, KOH, oops, sorry, something slipped there. Let me fix that. The rate of disappearance of KOH over time. In this case, I've got to keep track of this 2, so I'm going to put a 1/2 here as well. These two values are equal to each other. They're both equal to the rate. And I think you might be able to convince yourself of that if you were to actually think about what must the disappearance value of KOH be if H2SO4 was, say, 5. If H2SO4 was disappearing at a rate of 5, then the KOH would be disappearing at a rate of twice that. So if we were to take and solve this KOH for the rate, let me go ahead and just get rid of this, get a little bit more space. Let me show you how that would work. If I wanted to find out what's the, if this was 5, we'll just say 5 molar per second. Let's make it a really fast, crazy chemical reaction. If that's the rate of disappearance of this one, if this is equal to 5, then I think you're going to see that the delta KOH over delta T is going to equal -2 times 5 molarity per second. And so it's going to be 10. And well, actually, it's going to be -10, right? Which is what we'd expect. So if this is 5, this one's going to be 10 mole per second. And that's, I think, not too surprising since they're in that ratio of 1 to 2 already in the chemical reaction. All right, let's erase and move on. So here's another practice problem where we can look at the rate of formation of ethanol compared to the rate of consumption of glucose. What is ethanol? This is ethanol. How would you know this is ethanol? Well, it's being formed according to the question, so it must be on the product side. This is glucose. How is the rate of formation related to the rate of consumption of glucose? You can write inequality in terms of the rates. Once again, this actually is very easy if you think about the reaction having one rate. The rate of the overall reaction is going to equal each of these, so we could just write minus delta of glucose, C6H12O6, sorry, hope you can read that okay, and then over delta T is going to equal 1/2 times the change in concentration of ethanol, which is C2H5OH.
over delta t. So we can write an inequality that makes these two equal to each other. And then if you wanted to solve for one or the other, this is now an equation that you can solve. Assuming that you have delta t's for each one and you have some information, you could go ahead and solve for the rate of consumption of the one related to the rate of formation of the other, for instance. All right, that's a bit of practice with these rate laws. And what we're gonna, I'm sorry, let me back up. Those are not rate laws. Those were simple instantaneous or rather expressions of the rate of the reaction. And actually the reason I have this slide here is to remind me and to further explain to you the distinction between some of the terms that we're using. So what we were just doing is we were writing rate expressions. This is probably the most common way the textbooks in chemistry refer to what we just did. So, so going back, these things that we have here, this is basically just a very boring way to write the instantaneous or the current rate of a chemical reaction. It's kind of like saying like, well, how fast is the car going? You can just measure the distance it's traveling in a certain time. And by doing that, you're gonna write delta, delta x over delta t, and have a change in the x coordinate of the car. That's basically what the rate is, but it doesn't tell you much that's interesting about that car. What we're going to be doing next is we're going to be looking at what we call a rate law. And the law defines the relationship between the concentration of one or more reactants and a constant and the rate. So what we can do is we can now predict how fast the chemical reaction is going to be going if we know the concentration at a given time. So for instance, if you wanted to find out how to run your chemical reaction twice as fast, you might use a rate law to figure out, well, what concentration am I going to need to run this experiment twice as fast. For some experiments, it turns out you have to double the concentration to run the reaction twice as fast. For some experiments, if you double the concentration, the reactant might run 8 times as fast. And in cases like that, if you have an explosive compound or you have a dangerous compound or something that makes a gas, you might want to know before you do that experiment that you need to be very careful increasing the concentration. And in fact, there's many stories of chemists accidentally increasing the reaction too quickly because one of the concentrations was more sensitive than they realized. So a rate law is a fundamental relationship that is true across all temperatures between the rate of a chemical reaction and the concentration of one and more reactants. Now you might be thinking, well, don't products sometimes influence the rate of the reaction? Could a product, for instance, be appearing in the reaction mixture and either slowing the reaction down or causing the reaction to go faster? And if you're thinking that, then great, you should be a chemist. That's exactly right. There are cases where products can cause chemical reaction speeds to change. In this chapter and in this course, we're going to ignore all of those cases because they actually add a significant amount of mathematical complexity to everything that we're doing. So for now, to keep things simple, we're just going to assume that for all of our chemical reactions that only the reactants are influencing the rate. And so we'll look at a subset really of chemical reactions where that is true. And trust me, this will be complicated enough and interesting enough, I think, to really sustain us. Now, that's a rate law. We're going to spend a lot of time defining rate laws and deciding what they are. What I'll mention up front is that these need to be determined experimentally. You may be tempted to use the coefficients in a balanced chemical reaction to try to figure out like what's the rate law. And I think there's a bit of intuitive sense here because if a reaction is consuming one chemical at 3 times the rate of another chemical, you might think that that would really influence, the effect of concentration. Like if there's a chemical that's really in high demand in the reaction, maybe that chemical would end up in the rate law in some form. So I want to tell you, like, yes, that is actually chemically intuitively pretty good. I think you should follow that a little bit. However, what we find is that chemical reactions are very complicated, and sometimes what we're seeing happen between 2 reactants, there might be a bunch of other kind of more interesting sub-reactions happening where there might be intermediate products being formed. And in cases like that, we really can't take the coefficient from the balanced chemical reaction and make any determination of what the rate would be. So in this class, and I think for the foreseeable future, you should always just make sure that you're determining the rate laws experimentally. And I'll give you problems where there'll be experimental data and experimental information, and there might even be an activity where we have some experimental data that you can actually use to calculate this. Those are rate laws. Rates versus concentration, they're very useful. There's another type of rate law that we're going to see in this chapter called an integrated rate law. And these are, they're less, well, let me say this. They're exactly the same as the rate law, except that they're in a different form. What an integrated rate law is the rate law for a chemical reaction that has been mathematically transformed into a different but equally true version using calculus. So what's shown on the screen here below is an example of, I think this is a second order rate law and a second order integrated rate law. And in a case like this, what we see here is we no longer see the rate itself. So even though this is a rate law, if you look at this one at the very bottom, the word rate does not appear in here, and we don't have delta concentration over delta T anywhere, whereas we would at the top. You know, this rate that we have here, this is going to be the delta concentration, right? Some concentration value over delta T. That's what a rate is, as we saw in our earlier slides. But down here, there's nothing like this. This is basically just concentration at some time T versus time. So the two variables that are useful in the integrated rate law are concentration and time, and that's why we use these. If you have a question such as, how long will this environmental contaminant persist in my favorite waterway if it's being consumed by bacteria at a certain rate, you can use an integrated rate law to answer that question. You could, you know, say you want to find out how long it will take for 50% of that contaminant to be consumed, or maybe 90% of it to be consumed. An integrated rate law can help you to answer that question. And we'll do some problems like this in the course as well. It's probably good at this point to briefly walk through just a bit of the calculus as far as how we get these integrated rate laws. And let me see if I can get enough room here to do this. I'll try to do it in this little corner here. I want to show you how we might get something like this. Not this one, but another one. If you recall, a first order rate law would be defined as K times A, where A is one of the reactants and it would be raised to the first power. So we write the 1 right up here. And again, what I'm doing here is I'm actually relying on you to have gone and watched another video. We have another video that goes into, I think it's about 12 minutes of just really good examples about like what rate laws are. So this is a bit of a leap for you at this moment. Go back and watch that video and then come back. But this is an example of what we call a first order rate law. First order because of this number 1 that's in the coefficient of A. And it's very simple, right? It only has one reactant. And that's true for all of these integrated rate laws. They're all going to have basically just one reactant, because again, the mathematical complexity really increases if you start to try to deal with multiple reactants at the same time in an integrated rate law. So if this is the case, the rate is equal to K times the concentration. We can actually write the rate in that calculus sense of being D times the concentration over dt, and that's going to equal K times the concentration of A. And what I'm going to do next is I'm going to rearrange this equation, dA dt is equal to Ka, in a way that will allow me to integrate both sides. So maybe I'll sneak up here at the top. So if I multiply dt by both sides, I'll have dA will equal Ka dt. And now if I want to divide, I want to get dt on one side, so I just have time on one side of the equation, and I want to have the concentrations all on the left. I'll divide both sides by the concentration. And so my next step is going to be to look at dA over A. And that's going to equal K times dt. Now at this point, let me erase a little bit down here. What I can do now is, since I have one variable on the left and one variable on the right, I can basically, this is a technique in calculus called, what's it called? I think it's called separating variables. I can integrate both sides. And by integrating both sides, I can now integrate the left with respect to a over a certain time from 0 to t. And I can integrate the right with respect to t over the same time frame. And the integral of dA over a or dx over x, what that integrates to is the natural log of a. And if I'm going to integrate kt from 0 to t, I'm going to get, hold on, I'm having a hard time writing here, kt. And this one on the left is going to be integrated from 0 to t. Kt is also going to be integrated from 0 to t. And what that means is that I would basically have kt minus kt k0, right? So time at time 0, but time at time 0 is basically 0. So this term becomes kt. And let me get some more space up here. This term, if I've integrated from 0 to t, I'm going to have the natural log of a at time t minus the natural log of a at time 0, and that's all going to equal kt. This gives us the integrated rate law. I actually don't have it on this slide, but if you go to the book, you'll see that the first order integrated rate law is basically this form. And the reason I'm doing this right now is not that you'll be expected to do this. Even if you've had calculus, I'm not going to ask you to do these kinds of derivations. But what I wanted to show everyone is that the integrated rate law is exactly the same as the rate law, it's just in a different mathematical form. So they're not fundamentally different beasts. It's just that some mathematicians, really some mathematically savvy chemists have come in and they have adjusted this underlying equation in a way that gives us some useful results, especially if you're interested in running chemical reactions and finding out like when they're done. All right, that's it for this video. Thanks for your attention. I'll go ahead and post this as soon as I can, and more are on the way.